third line of the semester is measuring the distance dependence of the magnetic field of a bar magnet. Simply put, that as our scanner gets farther and farther away from our bar magnet, the magnetic field should get closer and closer to zero. This is proven by my results, because for R of 1000 we have 1000 U of t. For R of 1.5 R, for 1.5 R of 1000 we have 351 U of t. For R of 1.75 we have 240.72 U of t, and for 2R we have 174 U of t. We were also calculating our distance dependence, which is n, which I got as negative 2.5273. Models and formulas we use for this is to the right we have our magnet in blue, our phone in yellow is orange, and our magnetic field as the red arrows. And as you can see, as they get farther and farther from the magnet, they get smaller and smaller, or the magnetic field gets a smaller and smaller magnitude. For this equation, we had to use the on-axis magnetic field for a bar magnet, or a dipole in this case for a bar magnet, and which acts very similar to a dipole. We got mu naught over 4 pi times 2 mu over r to the third. This actually gets us our hypothesized distance dependent, which is what r is to, which is to the negative 3, since it's under 2 mu. Our value was negative 2.7273, which is very close to it. Over to the right, we also have our graph, which we got when we plugged on our numbers. But some of the reasons that our answer wasn't exactly negative 3 was there could have been just random errors in the experiment. For example, I had to measure most of this with my eyes and my hands, so it could have been off very slightly. Also, I tried to get away from as much electronic equipment as I could, but I couldn't get away from all of it. And since electrical components make slight magnetic fields of their own, could have skewed the data slightly. We also defined the 45 degrees measurement, which was we turned our magnet 45 degrees from the on-axis and hypothesized what it would be. I hypothesized that would be around 3/4 of what the on-axis one should be. My argument was because on axis the magnetic field is twice that of the perpendicular one, so halfway between those two would be around 3/4. As I experimented, I found my hypothesis had merit for it. For the below values, I have the actual and the expected, and they are around 3/4 of what my original on-axis measurements are. We had 2 questions for the experiment. The first was if I had laid my mirror stick, magnet, and phone that was not on a line that compensated for the Earth's magnetic field, how would our answer have changed? Our answer would have changed based on basically where I placed it, because the magnetic field of the Earth would have been read by the scanner and would have influenced the numbers. So our scanner wouldn't have just read the magnet's magnetic field, it would have read the Earth's as well, skewing our data. Also, our second question is if 2 identical magnets were stuck end to end and I repeated the experiment, what would I expect and what would I expect to happen? I expect that I would have to double the distance away from the magnets to get the same result, as the magnetic field would be twice as strong. Continuing, we have our Excel sheet. Over on the left, you can see all of our values, our averages, our B of X's. And then over on the right here, you can see our BX of 45 and all of my tested averages for what I got. And you can see they're around 3/4 of what I got for the distance, just regular B of X for the on-axis measurements. Below we have our graph, as you can see, and the rest of our data that I plugged in to get this graph. Lastly, this is our code. The orange arrows are the perpendicular and on-axis magnetic field of this experiment, and our white arrows are the 45 magnetic field of the magnet. As you can see on the left, below the actual picture is our magnetic fields for the on-axis perpendicular and 45. And if you take the magnitude of the 45 degree values, you get 452, which is very close to my predicted, which would have been 429 for for the magnitudes of the 45 compared to the magnitude of the on axis.